What if every possible you is real? Imagine me, Richard Feynman, sitting backwards on a chair in front of you, drums nearby, that mischievous glint in my eye. You know, people always ask me, Feynman, how does an electron get from point A to point B? And they expect me to say something simple like, well, it travels in a straight line, or it follows Newton's laws. But nature, oh boy, nature is far more interesting than that. The electron doesn't just take one path, it takes every path. Every single possible path you can imagine, and even the ones you can't. Now, before you think I've gone completely nuts, though I won't entirely discourage that suspicion, let me tell you a story about how I came to understand quantum mechanics in a way that nobody had quite seen before, the problem with the old way of thinking. When I was a young guy at Princeton, working on my thesis, I was frustrated. Quantum mechanics worked, don't get me wrong, but it was a mess. You had all these matrices, operators, wave functions collapsing. Schrödinger had his equation, Heisenberg had his matrices, and they were mathematically equivalent, sure, but they didn't feel right to me. They didn't give me a picture I could see in my head. See, I'm a visual thinker. I need to see what's happening. I need to imagine the electron, watch it move, feel what it's doing, and the standard formulation of quantum mechanics just didn't give me that. It was all abstract mathematics floating in Hilbert space, whatever the hell that means when you're trying to understand reality. So I thought there's got to be a better way, a way that connects more directly to what we can observe, to what actually happens in the world. Every path contributes. Here's the crazy thing I realized. When an electron goes from point A to point B, it doesn't choose one path. It explores all possible paths simultaneously. Imagine you're trying to get from your house to the grocery store. In classical physics, the physics of everyday life, you take one path. Maybe you walk down Main Street, turn left on Oak Avenue, and there you are. Simple, right? But an electron, that little rascal takes Main Street, and it takes Oak Avenue, and it takes a path that goes through Tokyo, and another that loops around the moon, and one that zigzags back and forth 1 trillion times, and another that spells out hello in cursive across 3 continents. Every single possible path. Now you're thinking, Feynman's really lost it this time. But wait, here's where it gets beautiful. Each path contributes what we call a probability amplitude to the final result. And here's the kicker. These amplitudes are complex numbers, which means they have both a magnitude and a phase. Think of them like little spinning arrows, each one rotating at a different rate depending on the path. When the electron takes a path that requires more action, and I'll explain what I mean by action in a moment, that path's contribution spins faster. When you add up all these spinning arrows from all the different paths, something magical happens. Most of them cancel out. The ones spinning wildly in different directions cancel each other, and what you're left with are the paths that are close to the classical path, the path that Newton would have predicted. What is this action, anyway? Now, I need to tell you about something called action. It's one of the most beautiful concepts in all of physics, and it's been around since long before quantum mechanics. The action is basically a number you can calculate for any path. You take the kinetic energy of the particle, the energy of motion, subtract the potential energy, and integrate that over time. Don't worry about the mathematical details. The point is that for every possible path, you get a number, the action. In classical physics, there's a principle called the principle of least action, which says that nature chooses the path with the smallest action. It's like nature is lazy. It wants to minimize effort. And this principle explains all of classical mechanics. You can derive Newton's laws from it. But in quantum mechanics, we don't say nature chooses the path of least action. Instead, we say that every path contributes and the contribution depends on the action. Paths with similar actions interfere constructively. Their probability amplitudes add up. Paths with wildly different actions interfere destructively. They cancel out. The result? For large objects, baseballs, cars, people, the quantum contributions from crazy paths are so tiny and cancel so perfectly that you only see the classical path. But for tiny things like electrons, those other paths matter. They produce all the weird quantum effects we observe: interference patterns, tunneling, uncertainty. The double slit experiment, every path through both slits. Let me give you the most famous example. The double slit experiment. You shoot electrons at a screen with 2 slits in it, and on the other side, you see an interference pattern, bands of light and dark. In the old way of thinking about quantum mechanics, people would say the electron goes through both slits as a wave, then interferes with itself. Or they'd talk about the wave function collapsing when you measure which slit it went through. It all worked mathematically, but it was conceptually murky. In my formulation, it's much clearer, or at least it feels clearer to me. The electron takes every possible path from the source to the detector. Some of these paths go through the left slit, some go through the right slit. Some, and this is wild, don't go through either slit at all. They bounce off the walls, loop around, whatever. But when you add up all the probability amplitudes from all these paths, the ones that dominate are those going through the slits. And the interference pattern emerges naturally from the way these amplitudes add up. Paths through the left slit and paths through the right slit can interfere with each other because they're all contributing to the same final event, the electron hitting a particular spot on the detector. When you try to measure which slit the electron went through, you're changing the experiment. You're adding new interactions, new paths, and the interference pattern disappears. Not because of some mysterious collapse, though that's one way to talk about it, but because you've fundamentally changed which paths are contributing to the final result. Time goes backward too. Here's something that really baked everyone's noodle when I first talked about it. In my formulation, you can think of particles as going backward in time, just as easily as forward in time. I remember sitting with John Wheeler, my thesis advisor, in his office, and we were talking about why every electron has exactly the same charge and mass. Every single electron in the universe is identical. Why? Wheeler had this crazy idea. What if, he said, there's only one electron and it's weaving back and forth through time? When it goes forward in time, we call it an electron. When it goes backward in time, we call it a positron. Now, this particular idea doesn't quite work for technical reasons. There aren't equal numbers of electrons and positrons in the universe, but the mathematical framework allows for it. In my path integral formulation, a positron is mathematically equivalent to an electron traveling backward in time. This isn't just mathematical trickery, it's deeply connected to the symmetries of nature, and it led to important developments in quantum field theory, where we really do treat antiparticles as particles going backward in time. What does this mean for you? Now let's get personal. Let's talk about you. You're not an electron, obviously. You're a collection of something like 10 power 28 atoms, all interacting with each other and with the environment in incredibly complex ways. But the same quantum mechanical principles apply. In principle, and this is where things get philosophically wild, you're also taking every possible path through space-time. There's a version of you that's sitting there reading this. There's another version where you decided to stand up right now, another where you never started reading this at all, another where you suddenly decided to do a handstand. But here's the thing. For something as large and complex as you, the paths that deviate significantly from the classical path cancel out with extraordinary precision. The probability amplitude for you suddenly teleporting to Mars is so infinitesimally small, with so many wildly spinning phase factors canceling out, that it effectively never happens. The action for a human-sized object following a weird path is enormous compared to Planck's constant, the fundamental scale of quantum mechanics. And when the action is much larger than Planck's constant, the quantum effects wash out, and you get classical behavior. But wait, the quantum you. However, and this is important, you're not entirely classical. Your brain, your thoughts, your consciousness, these emerge from chemical and electrical processes that ultimately depend on the behavior of individual molecules, atoms, and electrons. When an electron in your brain takes one path versus another, when a molecule binds or doesn't bind, when a neuron fires or doesn't fire, these are quantum events. They involve small enough scales and energies that multiple paths can contribute meaningfully. Does this mean that there are parallel versions of you exploring different neural paths? Well, that starts to sound like the many worlds interpretation of quantum mechanics, which Hugh Everett came up with. In his view, every quantum possibility actually happens in some branch of reality. My path integral formulation is compatible with that interpretation, but it doesn't require it. I always preferred to stay agnostic about interpretations. The mathematics tells you what you can observe and measure. The rest is philosophy. Interesting philosophy, but philosophy nonetheless. The unity of all paths. Here's what I find most beautiful about the path integral formulation. It reveals a deep democracy in nature. No path is forbidden. Every possibility contributes. The universe doesn't pick and choose. It explores everything. The reason we see the particular reality we see, with its apparent definiteness and causality, emerges from the interference pattern of all these possibilities. It's like a beautiful symphony emerging from the combination of many different notes, some harmonizing, some canceling out. When I was working out these ideas, I used to draw little diagrams, what people now call Feynman diagrams. They're pictures of all the different ways particles can interact. An electron emits a photon here, absorbs one there, creates a particle-antiparticle pair that annihilates. Each diagram represents a different path through space and time, and each contributes to the final probability amplitude. These diagrams became incredibly useful for calculations. My colleagues, guys like Schwinger and Tamanaga, who shared the Nobel Prize with me, were doing similar calculations using the more traditional approach, and they'd end up with pages and pages of algebra. I could do the same calculation by drawing a few pictures and writing down the corresponding terms. It was faster, more intuitive, and I have to say, more fun, the illusion of a single reality. So here's the thing that keeps me up at night, even now. The reality you experience, where you seem to follow one definite path through life, making one choice after another. That's an emergent phenomenon. It's what you see when you coarse grain over all the quantum possibilities. At a deep level, you really are exploring every possibility. The universe really is considering every option. But the way these possibilities interfere with each other, the way they add up, creates the illusion, or maybe it's the reality, who knows, of a single definite history. It's like watching a movie. The movie seems continuous, but it's really made of individual frames. And each frame is made of individual pixels. And if you go deep enough, each pixel's color is determined by quantum processes in the screen's electronics. The continuous, meaningful story you experience emerges from all this underlying complexity. Quantum mechanics and free will. People always want to ask me about free will. If every path is explored, if every possibility happens in some sense, then what does it mean to make a choice? I don't know. I really don't. And you know what? I'm not sure the question even makes sense in the way people usually ask it. Here's what I do know. You experience making choices. That experience is real. It's part of the data of the universe. And whatever is going on at the quantum level, whatever path integrals are being calculated by the universe's fundamental processes, they have to account for that experience. Maybe your choices are just complicated physical processes, and the feeling of choosing is an illusion. Maybe consciousness does something special that we don't understand yet. Maybe the question dissolves once you understand it properly, like asking, what color is Tuesday? The path integral formulation doesn't answer these questions, but it does show you that reality is far stranger and more interesting than our everyday intuitions suggest, the calculation that nature performs. Here's something that blows my mind. When I calculate the probability of some quantum event using the path integral formulation, I'm adding up contributions from infinitely many paths, literally infinitely many, and somehow I get a finite answer that agrees with experiment to incredible precision. But here's the really wild thing. Nature doesn't seem to be doing a calculation. When an electron goes from A to B, it doesn't pull out a calculator and sum up all the path integrals. It just does it. The behavior emerges naturally from whatever the fundamental reality is. So in some sense, the path integral formulation is just our way of describing what nature does effortlessly. We're calculating, but nature is just being. This makes me think that maybe our descriptions of quantum mechanics, whether it's path integrals, wave functions, or something else, are all just shadows of some deeper reality we haven't grasped yet. We're like people who've never seen a three-dimensional object, trying to understand it from its two-dimensional shadows. Every version of you is real, sort of. So, coming back to the question, is every possible version of you real? In the path integral formulation, every possible path you could take through space-time contributes to the probability amplitude for you to be where you are, doing what you're doing. In that sense, yes, every possibility is real in that it affects the final outcome. But most of these possibilities cancel out. The probability amplitude for the version of you that suddenly jumps 10 feet in the air is exactly 0 after you account for all the interference. So that version of you is real in the calculation, but it doesn't manifest in observable reality. The versions of you that are real in the sense of having significant probability are the ones close to the classical path, the ones that obey the laws of physics as we normally experience them. However, and this is the kicker, at the quantum level in your brain, in the chemical reactions in your body, there might be genuinely different possibilities that don't cancel out completely. A neuron might fire or not fire based on some quantum event. That could lead to a different thought, a different decision, a different path through your life. Are all these versions real? Do they all happen in different branches of reality? Or does one possibility somehow get selected and the others don't happen at all? The honest answer. You want to know what I really think? I think the question assumes we understand what real means, and I'm not sure we do. The path integral formulation is a computational tool. It's a way of calculating probabilities that matches experiment perfectly. But what it tells us about the nature of reality, about what's really happening, that's not entirely clear. Maybe every path is equally real, and we just happen to experience one particular sum of all those paths. Maybe only one path is real, and the others are mathematical fictions that we use to calculate what that one real path will be. Maybe the question doesn't have an answer because reality doesn't work the way our language and concepts assume. What I can tell you is this. The universe is under no obligation to make sense to you or to me. Our job as scientists is to find descriptions that predict observations, that reveal patterns, that connect different phenomena in illuminating ways. And the path integral formulation does all of that beautifully. Whether every possible you is real in some metaphysical sense, well, that's for philosophers to argue about over beer. As a physicist, I can tell you that every possible you contributes to making the actual you, and that's pretty damn interesting all by itself. The beauty of uncertainty. You know what I love about this picture of reality? It's the right amount of strange. It's not so weird that it's disconnected from everything we know, but it's weird enough to remind us that nature is cleverer than we are. The path integral formulation shows us that the universe explores all possibilities, but most of them cancel out, leaving us with the orderly, predictable world we experience. It's like the universe is an infinite improvisation that somehow produces a coherent melody. And maybe that's the real answer to whether every possible you is real. Every possible you exists in the calculation that produces the actual you. You are the sum of all your unlived lives, all your unmade choices, all your unexplored paths. They're all there in the quantum mechanical description of reality, interfering with each other, contributing their little spinning arrows to the final probability amplitude that is your existence. In that sense, you're not just one person following one path. You're a symphony of possibilities, most of them silent, but all of them present, all of them necessary to produce the particular note that is your life. And if that doesn't make you feel both incredibly special and cosmically connected to everything else in the universe, then I don't know what will. I'd grin at you now, pick up my bongos, and play a little rhythm, because sometimes the best response to the profound weirdness of reality is to make some noise and celebrate the mystery. The universe doesn't care what you think should be possible. It does what it does, and our job is to figure it out and enjoy the ride. Every possible path, every possible you contributes to the magnificent, strange, beautiful reality we get to explore. Isn't that wonderful?